Hi everyone, thank you for coming to the session. 大家好，我是来自英国伦敦帝国理工学院的俄罗斯人，我叫 Andrei。我现在正在努力学习汉语，我也非常喜欢火锅，但是伦敦的火锅，说实话一言难尽。我接下来会用英语做报告，因为如果用汉语的话，对我来说有点难。So I continue in English. All right, so today we will talk about developing markets for data and forecasts. And specifically, we will focus on practical engineering applications. How can we develop such markets for electric power distribution systems? And we are used to this idea that more data is always better. And the more accurate forecasts we collect, the more accurate decisions we will take. And while this is often true, it is not easy to estimate the real value of our forecasts. And that's why we have this idea of value-orienting forecasting. And today I will show you this idea with application to electric vehicles, load forecasting, and optimization in power distribution systems. I like to start with this quote: the usefulness of data is difficult to estimate in advance without applying it to a prediction or decision-making task. And I believe that this statement shows the true nature of data and the level of challenges that we have, because this is not a usual market. We don't know the intrinsic value of data or a forecast. To understand the value of forecast, we need to first collect it, use it in our model, then double check it in real-time operation, and only then we can see if it was useful or not and how much we can pay for it. So today we apply this concept of data valuation for electric vehicles load forecasting. And first let me tell you why we care about electric vehicles. So maybe you noticed that many electric vehicle charging stations are being installed everywhere in the world. And I found this nice colorful picture of a typical Shell recharge station. It has 4 charging points, and its peak capacity can reach more than 300 kilowatts. So that's quite significant for a local distribution network. It is equivalent to a load of around 70 houses. So we can imagine that we need to forecast to anticipate the load of this charging station, because switching it off and on is the same like switching off and on 70 households. But maybe you can say that this is not a very impressive picture, so I was searching online for the largest charging stations in the world, and I found this, the biggest charging station, Shell Charging Plaza in Shenzhen, China. So China is the leader for now. This place has 260 charging points, and its peak capacity is more than 15 megawatts. 15 megawatts is the load of a small town or some large factory. And here I think it becomes obvious why we need to optimize operation of distribution systems and why we need to anticipate loads from such high demand electric vehicle charging stations. Because if we don't do this, not only we can lose money, but also we can reach some unsafe operation of distribution systems. So that's why we are trying to create markets for EV load forecasts, and we are trying to estimate its value. But what would happen if we have several electric vehicle charging stations connected to a distribution system? This is the case we are working with, 33 bus distribution system with 3 electric vehicle aggregators. You can see we visualize the network as a graph where the size of each node corresponds to the load located at that substation. And we placed 3 identical electric vehicle aggregators in this system, connected to different parts of the network. And these connections are important because the network is not similar, it has different physical constraints. For example, as I show here in red color, we have some feeders with lower voltage profiles. This happens because these parts of the network are located further away from the primary substation, from the supply point, and therefore they experience higher voltage drop, and they are operating under lower voltage profiles. This is an engineering problem because if we want to consume more power for electric vehicles, the voltage will drop even further and the operation of the network will become infeasible, we can say unsafe. That's why we need to always respect this engineering constraint while supplying electric vehicles. And how do we supply them? You can see I put some dollar signs, dollar symbols here, because we assume that we can buy power from the primary substation, from the main grid, or from the flexible unit located deeper into the network connected to bus 7. And this unit actually can help us to mitigate these voltage violations and to improve the voltage profile. So we have two supply sources in this case. But where are the forecasts and how can we use forecasts for electric loads and electric vehicles demand? Well, we need some assumptions. We need to assume what is our initial understanding, baseline forecast for loads. And in this case, we say that the forecast that the system operator has originally, this baseline value, is quite conservative. It's 0.1 megawatt. So this is what we expect without any additional forecasts. But then each electric vehicle can provide improved forecast of 0.2 megawatts, and it is closer to the real observation of 0.25. So each EV provides an improved forecast, and it should be useful for us, right? If we can anticipate loads more accurately, we can improve our system operation. And note that, as I said, we assume that these three electric vehicles are identical. They have same power, same forecast, and same load observations. And system operator can use these forecasts to improve the operation. Now, how can we estimate the value of these forecasts submitted to the operator? It's not trivial to do so because we have a two-stage problem. First, we have day-ahead operation, so we collect forecasts. Here I say EV load forecasts, and we need to perform day-ahead dispatch. So we need to optimize our system anticipating these levels of EV loads. But then the real-time operation comes, the blue part of the figure, and if we have any mismatches between forecasts and real loads, we need to redispatch our system again. We need to perform balancing actions. And only after that two-stage method, two-stage approach, when we first collected forecasts, used them, and then we saw the reality, we can estimate the value of forecasts. We don't have time to talk about all equations and models, but I just want to say that if you want to solve the dispatch problems, you need some optimization models with the objective functions that minimize total generation cost or the cost of balancing actions. So this is a well-known part. The tricky part is this data valuation mechanism. How can we design it? And there are many methods known in the literature. The very trivial methods are accuracy-based, so we can say that we should pay more to the more accurate forecasts. But nowadays, many studies highlighted that accuracy is not the most important thing, and actually we need to think about the value of forecasts. So if we want to estimate the value, what metric should we select? And one of the popular metrics is avoided cost. So we have this day-ahead dispatch, balancing dispatch, we know the total cost. And we can compare the cost with and without our forecasts. And we should expect that with forecasts, the cost should go down. And we can use this metric to estimate the value of all forecasts and then to pay them. But still, we're missing the payment mechanism. And there are several, again, well-known solutions in the literature. And here I want to show you this method where actually we can use game theory to allocate the avoided costs between data providers. This method, I believe, was first proposed by MIT researchers Agarwal, Dalich, and Sarkar in the paper Marketplace for Data, where they claimed that we can use the Shapley value to allocate value of data for any machine learning model, for any prediction model. And actually, the logic behind the Shapley value is quite simple. We need to compute marginal contributions of each forecast. You can see this is simply the difference. So value with player I, which means value with forecast, minus value without this forecast. And then the Shapley value, the allocation of these payments, is simply a weighted average sum of marginal contributions. And it has some nice theoretic properties. That's why it's popular in the literature. Okay, so we performed this two-stage optimization. We computed the Shapley value, and this is what we see. We see that without forecasts, the cost was higher. Then we collect all three forecasts. The cost goes down a little bit, in this case by 28 euros per hour, which is not very significant, but this is also, keep in mind, this is a small network, so we have some savings if collecting forecasts. And then we compute the Shapley value. This is simply a vector of length 3 because we have 3 players, and it exactly allocates 28 euros between the 3 forecast providers. So the problem here, as you can see in red, is that the first player, EV22, is allocated negative payment, which basically means penalty. So how can this happen? We collected 3 identical forecasts. We know that all of them are improved forecasts. They are more accurate than our baseline estimation. And one of the players still gets negative payment. So first we thought that maybe this was some kind of a bug in the code. I was trying to fix that. But then we realized that this is the reality. This is what happens in the physical electric power distribution system. So we analyzed many dispatch solutions. On the right, I'm showing here the coalitional analysis. You can see players and their marginal contributions to the avoided cost. So the higher are the contributions is better for the, means the forecast is more useful. And we can see that indeed this first player is bringing some negative contributions, and that's why the Shapley value is -3, a negative payment. So while analyzing these solutions, I think we found the roots of the problem. And the problem is that in this system, there are 2 distinctive supply regimes. So first, we can supply our power from the primary substation. And the second regime is that we can fully or partially supply our system from the flexible generator. And the problem here is that transitions between these 2 regimes are expensive. If we underestimated loads, some loads, and we need to use flexible generator, we cannot just buy additional power from it. First of all, if we do that, we will pay more because it will be real-time balancing price. And second, if we want to increase power from flexible generator, we need to decrease power already dispatched from this substation because we cannot simply store power dispatched in the day ahead. So all these transitions are expensive. And why this EV22 located on the left is getting negative payments is because it is, in many combinations of forecast, it is pushing our solution to the wrong regime. So the correct regime here is to buy some power from flexible generator. But due to the forecast of EV22, even though it's accurate, we are pushing towards the wrong regime. And the Shapley value sees that. It sees some negative contributions, and therefore it's allocating the negative value to this EV, which is very counterintuitive. How can we penalize accurate forecast from one of the data providers? To further understand that, we performed a sensitivity analysis. So we gradually increased loads of all EVs, starting from 0 and up to 0.4 megawatts. And we also assumed that this time they're providing not accurate forecast, not improved forecasts, but perfect forecasts. So with 100% accuracy, we cannot hope for a better forecast, just perfect prediction. And here you can see the allocation of the avoided costs. So we are running multiple simulations while increasing the loads. And first, while we do that, we see that all these payments to 3 providers, they go together. And this makes sense because those are 3 identical perfect forecasts. But then after some point, these values diverge, and we can see that one forecast becomes much more valuable, while some forecasts go down and even become negative for our system. And this is what we saw in the previous simulation. So why this is happening? And we analyzed all parameters of the system. For example, here I'm plotting the voltage analysis, all voltages at all buses. And I highlight here in red the lowest voltage at bus number 18. And you can see that after some increase in EV consumption, we touched the limit. So this voltage constraint, this physical constraint got activated. And after it got activated, we cannot buy more power from the substation. So this line, this dispatch goes down, and we are starting purchasing more power from the flexible generator. So basically what happens here is that physical constraint got activated, and our identical forecasts are not same anymore. They don't have same value anymore. And one forecast is much more valuable. As you know, markets are repeated games. So to further analyze this, we performed 1,000 Monte Carlo simulations, assuming different accuracy of a forecast by 3 players. So each player provides a forecast uniformly distributed between 0.1 and 0.3. And we played this market game 1,000 times. So on the horizontal axis, you can see forecast error, and vertical axis, allocated payments. So the higher the payments means it's better for the player and it's bringing positive values. And this Monte Carlo analysis, I think, is very illustrative because we see that the purple player, EV14, always gets higher payments, and it has this tail of positive payments. While other players, for example, EV22, has a tail of negative payments, of penalties. So this is what happens when we apply a value-oriented forecasting and value-oriented market design. But my question here is that if we do this, we may systematically penalize accurate forecasts. And is this a good market design or not? Will forecast providers be happy to get negative payments or not? And as we can see, because of the physical constraints, the value can be very different. Before concluding, I just want to say that we expect to find similar effects in other applications, not only in distribution systems. If you think about any power system, for example, nowadays there is a trendy topic of wind generation forecasting. We want to buy data from many wind farms. Yeah, this will be useful for us, but what if some part of the network is congested? Maybe the value of wind from that part will be much more valuable, and value of other forecasts will go down and maybe will be penalized. And do we want to operate a market like that? Some simpler example, demand forecasts in logistics, in supply chains. Imagine you have several factories and demands, and again, some topology of the system, some operational constraints. What if, because of the forecast or because of some congestion, you need to perform expensive rerouting and redispatching of your goods? Then again, we can see this effect that some of the forecasts will become more valuable than others. So coming to the conclusion, as I said, forecast accuracy doesn't equal forecast value. So there is this idea that we need to perform value-oriented forecasting. But to do that, we need very complex models, two-stage optimization models, and these can lead to counterintuitive results. And the phenomenon that we discussed today is that we may have physical constraints. When they become binding, when they become activated, our data market, we can say, splits. Some forecasts become more valuable, and they become more valuable because of the costly transitions between the regimes. And if we have these unexpected shifts in the value of forecast, the question is it good for our market design or not? And I believe that further research is needed here. Thank you.
Okay, thanks, Andrew. So we still have like